Hello and welcome to the lecture Convolutional Neural Network Part 1. In this lecture, we are going to introduce convolutional neural network. Then we describe different architectural module, convolution, pooling, local contrast normalization of CNN. Then we try to understand a case study of image recognition through convolutional neural network. In convolutional neural network, we try to understand that this kind of network is used for particularly few purpose. In other words, we can say that a CNN or convolutional neural network is a specialized type of neural network. It is designed for automatic feature extraction and it is learn the input feature in a hierarchical fashion. And particularly it is useful for image-like feature. It is also used for other things, but other modalities like text and audio, such and such. But convolutional neural network is very useful for the image. So what is important here that it has the capability of automatic feature learning and it has a hierarchical design of feature learning. And that is one of the major aspects of deep neural network. If we go to understand a deep neural network, how deep neural network is different than a normal neural network or shallower neural network. From the architectural viewpoint, it is very simplistically. Number of hidden layers is higher for a deeper network. But if we see a bit closely, we can understand that the shallower net or conventional machine learning generally is a three types of work. One is feature extraction, and this feature extraction is manual or hand engineered. This may be geometrical feature, maybe statistical feature, maybe other features. But it is extracted or generated by human intervention. Then these features are subjected to the neural net or other type of machine learning, like support vector machine, like logistic regression, and so on. But in deep neural net, like CNN, this feature extraction and the inference or prediction, this network, data part and network part, are somewhat blocked. And it has a very interesting capability that it has automatic feature extraction, like CNN. So coming to the CNN to be specific, it consists of convolutional layers which apply multiple learnable filters or kernels across the input to identify the fundamental patterns such as edges, texture, shapes, and other simple physical structures. As we have discussed earlier also, that for a particular case of deep learning models like CNN. The initial layers are basically learns the very primitive pattern like edges, like textures, and like that. When we go into the deeper layers, it essentially model more complex features like shapes, more complicated. It is basically some object part and so on. So one thing is it's very important to understand in deep learning scenario when multiple hidden layer in place that we learn the features in a different layer of abstraction by a set of hierarchical learning layers or hidden layers. That is we have to understand important. So in CNN, unlike traditional neural network or conventional, each neuron in a convolution layer is connected only to a small local region or patch of the input, enabling the network to capture spatial relationship. Now, why it is so? If we consider an image, there is a very interesting property in image statistics. What is the property? That the image statistics or image, the nature of the image or the statistical features of the image are mainly homogeneous in a local neighborhood. So, if we use a small local region, you can put a particular neural kernel. There is a chance of homogeneity or homogeneous patches to find out what is the shapes, edges, and structures. So, this kind of architecture enabling the network to capture the spatial relations. Another important characteristics of CNN, a convolution neural network, is weight sharing. What do you mean by weight sharing? The same filter kernel or set of weights is applied to different region of input. This method significantly reduces the number of trainable parameters. So definitely, if the number of trainable parameters is reduced, the computational complexity is also reduced. Moreover, it improves the model's ability to generalize the answer data. So these are the some very important features that a convolutional neural network. It is our first step towards the deep neural network. And here we see some basic things that is not present in conventional machine learning approaches. That is the automatic feature and learn the feature in a different level of abstraction in a hierarchical approaches. And that is very important. Now we are going to understand the different modules of convolutional neural network. So, a CNN is composed of several fundamental building blocks that works together to learn hierarchical representation of data. So, if you see this picture, this is an image, dog, and these are the convolution modules. It is a low level module, the initial level, it's a mid level, it's a high level. This is a very hypothetical design. Now, one module is consist of this kind of. If we extend or expand this module, this we can say this is a convolution layer, pooling layer, nonlinear activation, normal, and so on. It is worth mentioning that for every module, all the submodules may not be present. Maybe in somewhere normalization is not present. That may be possible. But in general, these submodules are present in a particular convolution module. And such convolution modules are, here it is 4, maybe 40, maybe more than that, maybe 10, 15, anything. So as a whole, this is the convolution structure. Now, these features are given to the fully connected layers. In general concept, I say in general because that is, there is a very subtle difference between feature extraction and prediction. But in general, fully connected layers take this prediction task, and then values given to the softmax to get some probabilistic output. So as a whole, this is the whole structure of a complete CNN. Now we are interested about now one single module. Okay, so we start with convolution because this is the first layer. So convolution layer extract local spatial features by applying learnable filters to the input, enabling the network to detect patterns such as eggs, textures, shapes, etc. Now, what does this mean? We'll come in a more detailed picture what exactly happens. But for now, these convolutions are basically a function or a kernel function that is basically applied to the image batch to find out that if a certain feature is present or not. Maybe a horizontal line or a vertical line or a particular curve, a very simple curve. Some are very simple structure shapes and likewise. So this is convolution, the main. Next, although it is the pooling layer, is the most important. The pooling layer reduces the spatial dimension of the feature maps while preserving the most important information, thereby improving the computational efficiency and reducing uncertainty. Now, the one question you have to understand. Convolution layers are used to find out if certain features are present or not. But we require most or more dominating features. Pooling layers basically do that. That it basically try to understand what is the important most the patterns among all generated patterns. And definitely by this or by rejecting some patterns, it makes the feature maps smaller and thereby improving the computation complexity and chance of work. Next come the normalization and activation layers. Activation layers we know very well because activation layers impose some nonlinear or nonlinearity of this our hypothesis function. So basically this nonlinearity is used to learn complex feature representation. Another thing, the normalization. Normalization is stabilize the training process. What does this mean? Sometimes we see that the coefficients what is being generated by convolution is the range is very high. So sometimes it's required to make it a shorter range like +1, -1, 0, 1 and so on. Normalization is specific. So it's stabilizing the process. We'll discuss this in detail in this lecture. After this modules, when all these low, mid and high level extracted, these features are connected to the fully connected layers or just taken to. Fully connected layers integrate the extracted feature to perform classification or decision making task. And then these values come to softmax layer, final output to class probabilities enabling the prediction of the most likely class. Now combining these steps before fully connected and softmax, that it creates the submodule of a CNN. And after that, we put this fully connected and softmax layer, the whole CNN is designed. Okay, so it should address a wide range of computation tasks and data. Okay. Now we are going to understand the difference between conventional machine learning and the deep learning. And as an example of the deep learning, the convolutional learning. Now in conventional machine learning, we can observe that there is two main modules. One is feature extraction, another the network itself, which predicts some inference. Now in feature extraction, generally the human intervention is there. So you can say the ad engineering or feature engineering had engineered features, like feature may be geometrical features, statistical feature, some image patches, and many. Now whatever is the features, when it's been extracted, these features are subject to the neural net or any other discipline, and which predict some outputs. So this is the conventional way. So what important here to notice that there is two distinct parts. One is feature extraction, you can say data driven, and another is network driven. But in the deep learning, these two parts are somewhat clubbed. So this is a single network. This single network not only extract the feature but do this prediction. What this network do? So here, as we have mentioned earlier, the input layer, hidden layers, output layers, and in general, we can bit simplistically said that the initial layers, these initial hidden layers, are basically extract the feature. So there is a concept of automatic feature extraction, and the later layers, not very close to output layer, the fully connected layer or something. These are basically the classifier. So, but definitely there is no clear, you can say, separation there. It depends architecture to architecture, application to application. But for a hypothetical scenario, we can say that in deep learning, a single network handles both the work or both the task. And one important thing about this deep neural network is that is the automatic feature extraction. No human intervention is involved. No human is involved for feature extraction. The network itself extracts the feature, then this feature is put to the end of fully connected here and get the output. Now the question comes. This is an example of deep learning model. This is convolutional neural network. As we explained earlier, what is the basic modules, low level features, high level, mid level features. Now one thing that we have said earlier also, another very important concept of the deep learning is that we learn the features in a different level of abstraction. So some initial levels, so very this kind of initial hidden layers is basically involved to model the very primitive patterns. If we consider some geometric patterns, say lines, slanted line, some very simple curves, some very simple texture kind of thing. And when we go deeper, that's mid-level or high level, these hidden layers are basically model the more complex features. So one thing we can say that in deep learning, we model the feature at different level of abstraction in the hierarchically designed hidden layers. We can say low level, mid level, high level. We can put it on a single module here. It may be low level feature is multiple module. This is a multiple. So, and one module we have discussed in earlier slide that has a convolution layer, nonlinear activation, normalization, pooling, etc. So that is the basic understanding between a ant type and the difference between the conventional machine learning and deep learning, and definitely how a convolution neural network is being set up based on the concept of the deep learning. Now we going to understand what are the application of convolution matrices that is here. This first the convolution kernel and nonlinear activation, normalization, pooling, etc. So convolution kernels, as we mentioned earlier, are the fundamental components of convolution neural network that enable the automatic feature extraction from input data. Now, what actually, first we start with this convolution. So, this, how actually convolution works. Now, I read out, then we take some visual example or visual illustration so that we understand it properly. So by sliding across the input image, each kernel learns to detect specific visual patterns and generate feature maps that represent the presence of these patterns. So this is basically the idea. Now, different kernels specialize in identifying different types of features, allowing CNN to build increasingly complex representation through successive convolutional layers that we have mentioned here to here, here to here. And the major application include the edge detection, texture analysis, shape and object feature extraction, image classification. So importantly, the convolutional kernel serve as automatic feature extractor that progressively learn from simple low-level feature to complex high-level semantic representation. So this is very important, and that will be understood in very detail. So now first we start with this, how the sliding of image across the input image. Now take this visual illustration now. Here you can see that this is a convolution kernel, and what this kernel is, if you see 1 1 1 0 0 0 so minus 1 minus 1, so it's a zero crossing. Now when we are zero crossing means, it basically try to understand that in somewhere in this image patch there is some horizontal lines there on, because it's horizontal. So exactly this kind of, and this pattern you can see, this image pattern, this is all 4, the all 0, and there is a horizontal line, you can understand very easily. So how actually this kernel works? First, this kernel are basically on this 3 cross 3, this is put it, and element by element multiplication we are basically doing here, element by element multiplication, and we get that when it ultimately comes 0, so it's 0. So the resultant, and then the next thing is this is that we put one, so we sliding one position. Now this one position, when we slide it has a technical term that's called stride. Here stride is 1. Stride means we are sliding this kernel only one place, and we get another 0, and we do in this way. So again we can see from, we start from here and we go in this way, we are sliding in this way, okay? And we get all these zeros, and even we go here in this position, we can find plus. Again we can go in this way. So what essentially we get, that if you do this convolution kernel over this image patch, then the resultant kernel is this. Okay, so the thing is that this is the thing that we put this convolution kernel in this image patch, and we get this resultant pattern. Okay, so we basically do this, we get this kind of pattern, 0. So we find, yes, there is a horizontal line present. Now, if you searching for similar pattern that we can use some vertical filtering, you can use some vertical kernel, and it's horizontal filtering, some horizontal kernel, and the resultant edges is like this. Okay? So this is all about convolutions, how it actually works. Now, if we summarize that what the convolution is basically doing, we have some observation. First of all, the image statistics exhibit strong local consistency. That means in a local neighborhood, we have a similar image statistics. That here it is said in other words, it means that the pixels within a small neighborhood are highly correlated and often share very similar visual characteristics. And this is why we put a particular kernel on image patch rather than the whole image. So that is one of the major reasons of set up a convolutional kernel patch-wise. Next, CNN leveraged this property, applying a same set of learnable filter across different spatial locations. Now, it is also possible that let's see this image. Now, here you can see not only here also some similar characteristics, here also some similar characteristics. So, this kind of images where there is a large background or large homogeneous background, we can CNN leverage this property or these characteristics of the image by applying the same set of learnable filters across the different spatial locations through a mechanism called weight sharing. So here weight sharing is basically helpful because the resultant matrix are very similar. And it has a certain advantage. This enables the network to detect the same features such as edges, texture, patterns, regardless of their position in the image. And that is what we can understand easily from. In addition, for improving the feature extraction, weight sharing substantially reduces the number of trainable parameters. Definitely because we don't have to the other kernels. So same kernel, so same kind of weights. So making the model more computationally efficient and less overfit and better suited for processing high dimensional state. So these are the few things that what we observed. And CNN, that each hidden neuron is connected with small local portion as what we have observed in the normal image processing and computer vision task. And exactly CNN is doing this, known as receptive field. So each hidden neuron is connected to only a small local region to the input, known as its receptive field. I mean, this is here its receptive field, enabling the network to capture localized spatial features. That's what we observe in the local features. Similarly, the same set of learnable with the weight sharing that also been used by CNN. So this approach detects similar patterns regardless of their location as well and seen in a normal image processing or computation task. So any neural network architecture that incorporates one or more convolution layers is classified as CNN, the convolutional neural network, making it particularly well suited for image analysis, other tasks involving spatially structured data. That is bit interesting or important. This term, this image, is a kind of spatial data. There is no video data. There is no time involved. In DSP language, it's called pseudo-stationary signal. Spatial data is basically CNN is very much suited or very much suitable for this kind of spatial data due to these properties that So that's why we said that our CNN is basically very suitable for image. Now, with this background, we're going to build a kind of architectural understanding of CNN, or you can say convolutional kernels. Now, let's say if there is a fully connected layer. In this fully connected layer, this is 32 cross 32 layer, and as a 3 channels is there. If you say that RGB channel or any, and if you flatten data, say 1 into 32 into 32 into 3, it is 372. Okay, so this is a fully connected layer. Now, if this fully connected layer is multiplied with this weight vector, this is a W transpose, and it is 3072 cross 10. Definitely we're going to get 1 into 10 because it's just a product. So now what happened for this 10? These are different positions. So if we do just 1 into, if let's say for example, this is WT1, this is a 3072 into 1, not 10. We can get a single dot product, one scalar value. Since it is a 10, we can get a 10 out of this. So here, that this particular way these kernels are working. These are the scalar values for 1. So since it's a 10, so we can 10 scalar values. So a vector again with 1 into 10 with 10 elements. Now you can see what happened in the image. Image is basically, this is a 2-dimensional with a 3 the channel. So we use a 5 cross 5 into 3 filter. You can see this is not 2-dimensional. This is the filter is 3-dimensional. So this is also taken care of. And if you do this convolve or slide over all spatial location, since 5 cross 5 and 32 cross 32, we can get this activation map. And that activation map is 28 cross 21. 520 is maybe 28. That will see in the next slide how this equation is come. It is just coming because of it is taking every location and we put a single response out of it. Okay. Now the question was that from where we get this 28 cross 28 into 1. Okay. So the basic idea is that this is a image patch of dimension 32 cross 32, and we put the convolution kernel this 5 cross 5 into 3. So these 3 and these 3, so 3 channels. Now the basic formulation of this image patch size is n cross n cross 3, convolution kernel size f cross f3, stride 1, and output size k. Then this k is n minus f by stride plus 1. So this is the formula. So here n is equal to 32, f is equal to 5, stride is equal to 1. And if we put it, we get k is equal to 32 minus 27 by 1, and it's 27 plus 1, 28. So from where this 28 comes. So this is the basic idea. And since it is a single kernel, this is a 1. But now, if we put a multiple kernel here, if we put a multiple kernel here, let's say this is a 6 different kernels. Okay? That the patch is convolved with k different kernels, k is equal to 6. We can get these 6 activation maps different because kernels are different. We can get. hypothetical for our understanding. One kernel is for searching vertical line, one is horizontal line, one is slanting line, one is some sort of curve, and so on. And the similar activation is like this. Other things are also. So each activation maps detects a specific pattern defined by its corresponding kernel and k corresponding activation region maps. Now this is one, so it is 6 cross this. So activation is 28 cross 28 in one activation maps. So ultimately we can get that 28 cross 28 into this. If we can see here that we can use the pen, that this is 1 and this is 1, this is 1, this is 1, this is 1, this is 1. So ultimately this is 1 into this activation map into this into 6. So basically the total activation map, total number of activation map, if we say 28 cross into 28 into 6. So this is the basic hydrology here, because k is equal to 6. So that is the basic understanding of this. Okay. Now here we can use this, that input is 32 cross 32 into 3 image, and we can use this 5 cross 5 tool and 6 convolution kernel. So it is a map of 6 convolution kernel, 28 cross 28. Now we can use 10 convolution kernel. Now this is called 3 cross 3 we use, and 6. Again we use this, and basically 10 convolution kernel with 6, because this 6 for this and 3 cross 3, and we can use 26 by this formula. And we can use the 12 convolution kernel. Then 10 into, because this is 10, 3 into 3, and 12, 20, and so on. So in this way, the convolution is work in the subsequent layers. Okay. Basically the dimensionality is being changed in subsequent convolution layers by this. Okay. Now here, this the very interesting slide taken from the Justin Michigan online. Okay. That the activation map from AlexNet. So AlexNet we'll see later. This is a very important convolution neural network. First there are 64 filters, 3 cores, 3 into 11. So this basically the similar, that these are this 64 filter means 64 different kernels are being used of size 11 plus 11. So we get this. Anyway, they make it a visualization of what are the basically response of this kernels, and get this. Okay, so this is the same thing what we have studied, but this way can be this activation maps. Our next topic is pooling. As we have mentioned that while convolution determines whether specific patterns or features are present in the input, the effective feature representation also requires a mechanism to emphasize the most important patterns at its spatial location. What does this mean? What convolution do? Convolution is basically determine a particular pattern is present or not. But there is some requirement that which out of which these patterns are most dominating. most effective. So for effective feature representation, it is required to emphasize the most important patterns of expression, and this particular done by pooling. So pooling fulfills this role by selecting the most prominent feature response, such as maximum activation in a local neighborhood through max pooling. And sometimes we require some average out of it. We can do the average and so on. So by retaining only the most significant activations or response, pooling reduces the spatial resolution of the feature maps. Definitely, because it is only taken the most important one while preserving the most informative features. This process not only decreases the computational complexity, but it enhances the network's robustness to small translation and distortion in data. So this is another important. We'll see later that how this pooling procedure gives some sort of translation invariance in case of this kind of processing the images. Okay. Now let's try to understand what are the different types of poolings. So max pooling, average pooling, and why pooling is at all required. So first we'll start with max pooling. It selects the maximum value from each pooling region. So here you can see that this is 3, 8 equals 1 by 5, and this is this thing. So we can say that 8 is highest here. So retains that strongest feature response. Okay. So here you can see that we get 3, this 9 out of this. This we can see that 7 out of this. We can see that we can 6 out of this. So this is called max pooling. Next comes the kind of average pooling. Average pooling computes the average value in each pooling regions. That this is the 5. Similar thing is average it out. That's if you take the average 12 plus 4, 16, 16 by 4 and something like that, we get this, and so on. So on. Now, what or why pooling is necessary? It reduces the spatial dimension that we have seen. That just retaining the most important information speeds up the computation because computational complexity is reduced. Preserve the important features, improve robustness to the translation and reference. So some short of as a small translation invariance and noise reduction step. The next thing is contrast normalization. Contrast normalization is a technique in CNN that enhances the feature detection by normalizing pixel intensities or feature activation based on local contrast. It highlights the important features, suppresses uniform high intensity region, and improves the robustness to the illumination. We read out this and we try to understand in subsequent slide what these things means or these statements. And a common approach of LCN, that is local contrast normalization, is neighboring pixel or local subtraction. Now see what this trying to say. Now you take this kind of images. Contrast variation change pixel intensities and convolution response. So contrast normalization reduces their impact enabling more robust and consistent feature detection. You can see that if the contrast of image changes, you can see this, you can put these points, you can see this, why this point we put, that these are there. So the contrast are in these points are different in these pictures. So if the contrast of an image changes, CNN output may vary because filter response changes. Contrast normalization addresses this by adjusting pixel intensity to balance local brightness and contrast, reducing the effect of illumination variation, enhancing the structural details in the image, and improving the feature consistency across different regions. Now, if we just see these point positions, here the contrast are different, indifferent. Now, but basically this, the same image, kind of, if the same image with a different lighting condition we take, the response should be same. But if this kind of thing happen, then this basically the response will be different. That should not be happen and it should be avoided. The local contrast normalization is basically this. Okay, now see. So local contrast normalization reduce the illumination variation. That you see. This is a low light condition. This is a bit light is high. Use the effects of illumination variation by normalizing feature activation with respect to the local. So this process scales feature values based on the statistics of surrounding activation, making the network less sensitive to local contrast. Generally, they put this equation I of x minus and f of m k of standard deviation of k. As a result, this local contrast normalization enhances the age and texture information while suppressing the irrelevant intensity variation, allowing more discriminative features to be learned. By improving the consistency and robustness of the feature notion, LCN and to contributes to better generalization and overall performance in image recognition. So that what we have discussed, it is written in a very lucid language that basically even if there is some sort of lightning difference LCN, this normalization make it a similar response out of it. So if we summarize the CNN processing stage, that we can find a convolution neural network processes data through a sequence of specialized stages that progressively extract and refine it. That's what we can say. We progressively feature. It begins with convolution and the learnable filters applied to the input local pattern that we have seen. The resulting feature maps that pass to the activation function. That activation function generally use sigmoid, ReLU, and so on, which introduce nonlinearity and enable this network to learn complex data. Then normalization, this contrast normalization is something like this, to standardize the feature activation, improving the training stability, accelerating convergence, and enhancing the model's ability to generalize data. That also we have seen that. Finally, pooling stage downsample the feature maps, retaining the most important or significant activation response, thereby reducing the spatial dimension, lowering computational complexity, improving network robustness to spawn transmission and distortion. So as a whole, CNN do this, and we have discussed all this in very details in this the lecture. And the whole picture, if you say that what is CNN look like, a standard chain architecture consists of convolution layers that we can see, these are the convolution layers, and extract feature activation function, introduce nonlinearity. That the optional normalization layers that stabilize the inputs of feature consistency. Pooling layers reduce spatial dimension for convolution. components what to progressively learn, hierarchical feature representation, that is very important. The extracted feature being passed to the meg layers and final output for software classification. So as a whole, and you can say the accuracy or the performance of this is very high. So ImageNet 5 channels, then accuracy and classification. It resonates in 152 layers. This is a very and 60 million parameters. So this is the basics. So what is CNN for image recognition? That for our this particular course, we will basically try to understand different aspects. Object, how CNN is used for object detection, semantic segmentation, image class. New object detection, generate region proposal, localize objects and classify each proposed region using dedicated classification methods. Assign class levels to every pixel to them, such as image classification is single level to entire image, foundation for many computer vision applications. We see these things from generative AI viewpoint. Okay, so these are the general things that is generally image CNN is used, but we basically so summary, we in this chapter we introduce the CNN, then we discuss in detail convolution and we try to understand as an image recognition. And in the next lecture, we are going to discuss different CNN model architectures, which are very popular, such as PGGNet, AlexNet, ResNet, GoogleNet, etc. Thank you very much.